Welcome to polynomial functions. Now let's go over the steps to graph a polynomial by hand. Our first step is to determine the end behavior using the leading term test. The second step is to find and plot all x-intercepts, and how we do that is by setting the equation equal to 0 and solving for x. Our third step is to determine the multiplicity of each 0 and use this to decide if the graph will cross, bounce, or wiggle at each 0 or x-intercept. Our fourth step is to find and plot the y-intercept. And to do this, we just substitute 0 for x and simplify. And our fifth step is to plot any test points needed and finish drawing the graph. Now let's look at example 4. For example 4, we're asked to graph the polynomial p of x equals x times x minus 2 squared times x plus 3 cubed times x minus 1. And this one's really nice because it's already factored for us, which makes finding the zeros a lot easier. So we're going to go ahead and proceed with our first step, is to determine the end behavior using the leading term test. So to do that, it's actually easier for that test to see it in non-factored form, but even in factored form, we can still find out what the leading term is. And we can get that by multiplying the leading term of each factor. So I have x times x squared, because we have an x and then it's squared, so the leading term will be x squared there, times x cubed, because this for this x plus 1 factor, we have an x that's cubed as our leading term, times just x. For x minus 1, that's just a power of 1. And just remember, if it's just x, that's x to the 1. We learned about exponents, when you multiply the same base exponent, you add the exponents. So 1 plus 2 is 3, plus 3 is 6, plus 1 is 7. So our leading term here is going to be x to the 7th. For x to the 7th, notice that we have an odd exponent and a positive coefficient of 1. So let's look back at our leading term test. If we have a positive coefficient, so a is greater than 0, and if n, the exponent, is odd, the end behavior that we have is that we have arrows going up in the first quadrant and they're going down in the third quadrant. So we'll go ahead and draw that in kind of to get an idea of what the graph is going to do towards the extremities of x. All right, the next part is that we want to find and plot any x-intercepts. So we're going to go ahead to do that. We set our equation equal to 0. So we're going to have x times x minus 2 squared times x plus 1 cubed times x minus 1. We're going to set that equal to 0. And so to solve this, to set it equal to 0, basically any of these factors can equal 0 for that to be true. If x minus 1 equals 0, and we multiply it by the rest of the equation, it's going to equal 0. And the same for any factor. That's a zero product property, by the way. So all we need to do then is set each factor equal to 0 to find our x-intercepts. So if I take x and set it equal to 0, I'm going to get x equals 0. If I take x minus 2 and set it equal to 0, that just means that I'm going to add 2 to both sides. And I'm going to get x equals 2. If I take x plus 1 and set it equal to 0, that just means that I'm going to subtract 1 from both sides. And so I'm going to get x equals -1. If I take x minus 1 and set it equal to 0, then I'm going to be adding 1 to both sides. So I'm going to get x equals +1. But now that we know our zeros, well, we want to plot the x-intercepts associated with them. Now remember, at the x-intercepts, the y value is always 0. So when x equals 0, we're going to have the point 0, 0. At x equals 2, we're going to have the point 2, 0. At x equals -1, we're going to have the point -1, 0. At x equals 1, we're going to have the point 1, 0. And so let's go ahead and plot those points. So here's the point 0, 0. We have the point 2, 0. We have the point -1, 0. And we have the point 1, 0. The next step is to determine the multiplicity of each 0 so that we know how the graph behaves at that 0. So for x, for this factor right here, the 0 associated with it is 0. The multiplicity is just 1 because the exponent on x is 1. And we recently learned that what happens if the multiplicity is 1 is that the graph is going to cross straight through that 0. So at the point 0, 0, the graph is going to cross straight through. Notice for the factor x minus 2, we have an exponent of 2. So at x equals 2, our multiplicity is even, which means that the graph will bounce off of 2, 0. For factor x plus 1, we have a degree of 3, which is an odd number greater than 1. So the graph is going to wiggle across x equals -1. The factor x minus 1 has an exponent of 1, so the graph will cross straight through x equals 1. Our next step would be to find the y-intercept. But notice that the graph has an x-intercept of 0, 0 here at the origin, so that's also the y-intercept. So we don't need to do anything for that step. And then the last step is to plot any test points needed and finish graphing the polynomial. So test points are nice because they let us know how high or low a graph is going in each of our intervals. Like we have this interval from -1 to 0. We don't know how high or low it's going to go when we get to graphing it. So we want to plot test points in each of those. So we have this interval from -1 to 0. We have an interval from 0 to 1 and an interval from 1 to 2. And we're going to do test points in each of those. In the interval from -1 to 0, a nice center point is just -0.5. And you can use your calculator to do this, but you want to find p of -0.5. And that is approximately 0.6. So on our graph, we have the point -0.5, 0.6. And we can go ahead and plot that. -0.5, 0.6. That's about right here. Now let's find a test point in the interval from 0 to 1. A nice central point is 0.5. So we're going to calculate P of 0.5. We have P of 0.5. When you put that into your calculator, you're going to get approximately negative 1.9. So our test point has the coordinates 0.5, negative 1.9. And we'll go ahead and plot that point. It's about right here. Our next interval that we need a test point in is the interval from 1 to 2. And a nice central point is 1.5. So we're going to go ahead and find P of 1.5. And that is approximately 2.9. So our test point has the coordinates 1.5, 2.9. And we can go ahead and plot that. So 1.5, 2.9 is just shy of 3 up here. And now it's time to go ahead and connect our graph. So we know that our polynomial is going to originate down here in the third quadrant because we looked at the end behavior. So our graph is going to come up from the third quadrant. It's going to cross with a wiggle through x equals -1. It'll go through our test point, and then it'll go straight through x equals 0, down through the next test point. It'll go through straight through x equals 1, through the next test point, and then it'll bounce off of x equals 2. And then we can go ahead and erase these arrows that let us know where the end behavior is. We don't need them anymore. I'm going to go ahead and extend this down further. Here's a nice picture of the graph of our polynomial using the calculator, and you can see that it closely matches the polynomial that we drew by hand.